All right, chemistry 3111. So I was unable, or the recording didn't work for the last section, which dealt with the nomenclature question all the way up to the end of section 20.8, except for this question. And so I replaced it with a video, an old one on the playlist, and it says Chem 3111 lecture, and it was from October 21st, 2020. Okay, so I put that in the playlist, so it should be in there, and it's got a little extra work in it, but all the content should be in there. All right, so let's go over this first question. We take an acid chloride, we treat it with excess lithium aluminum hydride, followed by treatment with water or acid. Aqueous acid is fine. And what do? We end up converting the acid chloride to a primary alcohol. So we go from an acid chloride to a primary alcohol, like that. And so we end up with something that looks like this. Okay, so we end up with this alcohol. So that would be what? 2-methyl-1-butanol. Anyhow, the next one, we take an acid chloride and we treat it with excess phenylmagnesium bromide. So remember, it's going to add once, and then we're going to generate the tetrahedral intermediate. We lose the chloride, we form a ketone, and a second equivalent of the phenylmagnesium bromide is going to react with that. And we said that we were going to change the water to aqueous acid like this. So it's going to add twice. And so we end up with a tertiary alcohol. And now we're going to have two phenyl groups attached here like that. So there you go, a tertiary alcohol. Let me just move this down maybe a little bit like that. There we go. It's a little bit better. And the next one is, there's a couple of reactions here, aren't there, right? The first one, we're going to treat the acid chloride with lithium tri-T-butoxy aluminum hydride. So that's going to reduce the acid chloride down to an aldehyde. So let me just move this up here and we'll reduce that down to an aldehyde. So we're going to get cyclohexane carbaldehyde in the first step. Then we're going to treat that with ethyl magnesium bromide, followed by treatment with aqueous acid. So we'll scratch that out. So the ethyl group is only going to add once because it's on an aldehyde, and we don't have a leaving group on there. And so we're going to end up with a secondary alcohol. So we have this carbon, we have the ethyl group, and then we have our alcohol like that. So there you go. Now we've finished acid chloride. They're the most reactive of all of the carboxylic acid derivatives. So let's move on from acid chlorides to acid anhydrides. And one of the first reactions that anybody learns about acid anhydrides is how to make acetic anhydride. And acetic anhydride is actually a reagent that we use sometimes. And we abbreviate it like this, AC2O, like this. So there's two acetyl groups, right? There's one here, and then there's one here, and then you have an oxygen in between them. So we say, let me just rewrite it here in red maybe. So we use AC2O like that to represent acetic anhydride. So if you take acetic acid and you heat it up really high, 800 degrees, that's a lot of heat. You make acetic anhydride and you drive off water. The only thing about this reaction is it says here it only works well for acetic acid because other carboxylic acids can't survive the extreme temperature. And so really this is just kind of a one-off reaction. It's just good for this one thing to make acetic anhydride. But if you want to make any other kind of anhydride or an asymmetric anhydride, a more practical way of doing it is by taking an acid chloride, okay, and treating it with a carboxylate, because the carboxylate is a good nucleophile, isn't it? And you see the mechanism down here at the bottom, right? We have our nucleophilic attack. We form our tetrahedral intermediate, so tetrahedral intermediate, and then we lose chloride as a leaving group, and we form our anhydride. And of course, in this case, you'd also end up with sodium chloride, right, at the end. Okay, so you can see that over here. So given that an acid chloride and an acid anhydride both contain a good leaving group, right? Whether you're thinking about a chloride, a chloride is a good leaving group, and a carboxylate. So a carboxylate, they're both the conjugate bases of acids. One from a strong acid, one's from a weak acid, but they're both the conjugate bases of acids. And so they're both good leaving groups. All right. The difference between the two, or one of the difference, is that when we use an anhydride instead of an acid chloride, we do not have to use pyridine. It's not necessary to use pyridine with an anhydride because you don't end up making a strong acid. You just end up making a carboxylic acid derivative, like a carboxylate or something. So it's not strong, so we don't have to worry about it doing any kind of funny reactions with any other groups. So I might provide some more detail on that later on, depending on whether we have the time or not. But let's move on and let's take a look at all the reactions that can occur for acid anhydrides. And if you're sitting there at home and watching this video, if you're in class with me right now and you're thinking, well, that was pretty fast, okay? You're right, it was very fast, okay? Because a lot of the chemistry that we saw with acid chlorides, all that stuff that we learned in section 20.8, most of it applies here, right? Because again, an acid chloride contains a quality leaving group, and so does an anhydride. It possesses a quality leaving group. So let's take a look at all of these reactions. The first one that I showed you was that if you just heat acetic acid really hard, you're going to make acetic anhydride. Okay, fair enough. So if I make acetic anhydride, you can actually put it in water and it's going to blow it right back. It's going to hydrolyze the whole thing all the way back to acetic acid. Not the most useful reaction in the world, but acetic anhydride, it's so reactive with moisture that even if you open up a bottle of acetic anhydride, just the moisture in the air will react with it and convert it back to acetic acid. And so acetic anhydride will even smell like vinegar. It has that vinegar odor to it. Okay, if you're wondering about this reaction, so what happens in the first step here is if you treat a carboxylic acid with sodium hydroxide, you make a carboxylate, right? In this case, it would be a sodium carboxylate. And then that's going to react with an acid chloride. That's a reaction we already looked at to make an anhydride. Now, we said that if you take an anhydride and you react it with an alcohol, you don't need pyridine because you don't end up forming a strong base, or sorry, a strong acid as a byproduct. So you just need the alcohol and you're going to do the acylation reaction. Now, we also said that these three reactions, the aminolysis, they all follow the exact same mechanism. And so there's no difference between any of these. Again, we need excess of the amine, whether it's ammonia, primary or secondary amine, to make the primary, secondary, or tertiary amide. And that's to neutralize the product or the intermediate formed at the end. Then we have the lithium aluminum hydride reduction. I said we were going to replace this with aqueous acid, and we looked at that reaction. The reduction of the anhydride down to an aldehyde, we can do that the same way we did with an acid chloride. We just use lithium tri-T-butoxy aluminum hydride, follow that up by treatment with aqueous acid. Same thing with the Grignard, exact same reaction as with an acid chloride. We just acidify with aqueous acid at the end, and it's the exact same thing with a Gilman. And so again, I just want to repeat this one more time before I switch slides. Right before, what we saw was the chloride being a leaving group, and now really the only difference is we have this, and now our leaving group is going to be a carboxylate. So that's why so many of the reactions are analogous. So many of them are basically the exact same thing. All right, are there any questions about any of those before we move on and we get into well, actually, we're going to continue on with anhydrides. I have a couple more things I wanted to show you. So let me show you a couple more things about anhydrides. And I told you that acetic anhydride is actually used as a reagent. Okay, remember, acetic anhydride is the simplest of all the anhydrides. It's this guy here, and we sometimes label it AC2O like that. We actually use that to do what we call acetylation reaction. So you can acetylate an alcohol, or you can acetylate an amide. And the reason why this reaction kind of gets its own slide is because it's very common to do acetylation reactions. In fact, two drugs that you would know use acetic anhydride to do acetylation reactions. One would be the synthesis of aspirin from salicylic acid. So this is this compound here. This is salicylic acid. And then if you acetylate the alcohol or the phenol, You make aspirin, acetyl salicylic acid. I won't write that down. And then you can take para-aminophenol and you can make paracetamol, which is acetaminophen or Tylenol. Anyhow, so two reactions that involve acetylations. There are others as well that I'm not going to go into, but that's why you need to know acetic anhydride, because it's such a common reagent, right? Acetic anhydride, very commonly used as a reagent. So with all that in mind, let's take a look at a couple of reactions here. You can see this first one is the anhydride of benzoic acid. So this would be benzoic anhydride. So we could practice our nomenclature. Benzoic anhydride. And I'm not going to draw the full mechanism here, but one point I do want to make is we could just draw the first curved arrow, right, which is our nucleophilic attack, and then we form our tetrahedral intermediate. Now, again, I'm not going to draw the whole mechanism, but the idea is this, is that we end up with our phenol, okay, and what do? We add an acetyl group to it, or an acyl group to it, I should say, and so we end up with the acyl group. Now, the reason why there's no pyridine, okay, you don't need pyridine, is because the byproduct that's going to be formed is going to be benzoic acid, right? We form benzoic acid, which is not a strong acid, and that is why we don't need pyridine, because benzoic acid is not going to have any kind of adverse reactions with anything, and so you don't have to stress about making benzoic acid as a byproduct. Okay, let's try drawing the mechanism of B just to get some more practice here. So I'm going to switch over to a blank document here, so just bear with me. Come on, there we go. So let's find some space down here and let's give it the old college try. So this is question 20.19. And this is B. So we have propionic anhydride. I'm just going to write it a different way here, and you might want to write this reaction down with me. Oops. And what we're doing is we're reacting it with excess. So this is called diethylamine. It's just an amine with two ethyl groups on it. Okay, and this is an excess. So we have more than enough of it. So let's draw the whole mechanism. So we have our nucleophilic attack. We form our tetrahedral intermediate. So let's draw what that's going to look like. So we've got our tetrahedral intermediate. We're going to have our anhydride here, and then we've got our amine. So we have two ethyl groups, and then we have a hydrogen. So we have a positive charge here. Now remember, this is a good leaving group, right? It's the conjugate base of an acid, not a strong acid, but it's the conjugate base of an acid. And so we're going to lose the carboxylate. So let's lose that. And we end up with this. So now we've got our double bond restored. We've got our amine with our two ethyl groups, and it still has a hydrogen, so it's got a positive charge. And then we also end up with this carboxylate. And so what's going to happen at the end is that the carboxylate is going to, and I should put my lone pairs in, I am the instructor. Our carboxylate is going to abstract the proton and restore neutrality to the amide. So we're going to end up with this compound. So we end up with NN-diethyl propionamide and propionic acid. And again, propionic acid is not a strong acid, and that is why we do not need pyridine in this reaction. Give me a thumbs up if you follow me on that one. Or any questions about that mechanism? Okay, cool. All right, and again, if you have a question, don't hesitate to type it in the chat or interrupt me. It's not interrupting me, it's just asking me a question. All right, because that covers the section on anhydrides. So now we're going to get into esters. Maybe I shouldn't have done that. But I just wanted to get the point across that the section on esters, I'll talk about it while I'm trying to find my place here. The section on esters is of extreme importance. And I know I say that about a lot of things, but I'll tell you why. To me, this section covers the most important mechanisms in all of organic chemistry. And lots of people would probably argue with me on this because they'd say, well, no, the most important mechanisms are SN1, SN2, E1, and E2. Okay, I get that. But as far as big mechanisms that we look at that you have to know that get asked routinely on standardized exams like MCAT, DAT, PCAT, ACS. My quiz is, Dr. It doesn't matter who you take organic chemistry with. There's three things in the ester chemistry section that I think are really important. One is Fischer esterification. Fischer, okay, so we'll look at that. And the other one is hydrolysis of an ester. And we look at two ways to hydrolyze an ester. One is an acid, one is in base. The hydrolysis of an ester in acid is just called the hydrolysis of an ester in acid. But I'm telling you, that's what it's called. The hydrolysis of an ester in base is called saponification. So Fischer esterification is the formation of an ester. And then you've got hydrolysis in acid and hydrolysis in base. To me, those are just some of the most important mechanisms in all of organic chemistry. But we're going to start here with this reaction, which is not one of those reactions, but it is a way to make an ester. I don't know if I've ever done this reaction in my life. Probably have and don't remember. But this one, do you guys remember the Williamson ether synthesis? It's definitely not the same thing, but it kind of reminds you of that reaction in a way. Because what you do in the first step is you treat a carboxylic acid with sodium hydroxide. Well, what's that going to give you? That's going to give you the carboxylate, right? Like that. And then in the second step, you treat it with iodomethane. And so that just reacts via an SN2 like that. So, is it a good way to make an ester? Sure. And is it like a Williamson ether? In a way, I guess. But again, I don't know if I've ever done that reaction in my life, but kind of a neat way to make an ester. Now, again, I think this is the most important mechanism in all of this class. And I mean organic 1 and organic 2. It's the mechanism of Fischer esterification. It's the combination of a carboxylic acid and an alcohol with a catalytic amount of acid. You form an ester and you drive off water. So let's review. You take an acid plus an alcohol. You use an acid catalyst, a strong acid catalyst like HCl or H2SO4 or something like that. You make an ester and water. And of course, you can remove the water from the reaction mixture using a special apparatus to do this. Now, you want to be able to draw the mechanism of this reaction. And I think that I have a question later on where we do not we draw the hydrolysis of an ester. But this is one of the most important reactions in all of organic chemistry. So you know what? Let's go over to a blank document and draw the whole damn thing. Pardon my language. Come on, Mr. Dion, what are you doing? All right. I think this is such an important reaction. Let's just park it here for a second. So Fischer esterification. Now, what was one of the main focuses or foci? I don't know. Of this chapter was nucleophilic acyl substitution, right? So if we're starting out with a carboxylic acid, okay, and an alcohol with a catalytic amount of acid. So remember, we put catalytic amount of acid, right? And then we end up forming an ester. So in this case, it's a methyl ester, and we liberate water. Now, what's the major acid species in solution here? Can anybody tell me what's the major strong acid that's going to be in this reaction mixture? Not the carboxylic acid, no, because the acid catalyst is a strong acid. So what's the major strong acid that's in solution? When you mix all these things together, no, it's not H3O plus, not in this case. Not the carboxylic acid, it's not H3O plus. So what's the solvent here? The reaction is not done in water. It's done in methanol. Okay, and you can't just have a proton by itself. So look, we have a mixture of methanol plus a strong acid, right? So that strong acid, again, it could come from something like sulfuric acid. So there's going to be an equilibrium between this and the protonated form of methanol and the hydrogen sulfate ion. So this is going to be the major acid catalyst in solution. It's going to be a protonated methanol molecule. So what's the first thing that's going to happen? Let me ask you a question. Can methanol Based on what we've learned today, can methanol just attack this like that? Would that be proper? Would those be proper arrows? The answer is no, no way, because you'd end up with a negative charge. So what's the first step of the mechanism going to be? Really getting into it here. What's the first step of the mechanism going to be? It's going to be a protonation of the carbonyl, isn't it? Of the oxygen on the carbonyl. So let's draw our acid catalyst and let's protonate that carbonyl. So we end up protonating like this. And I'm going to put the mechanism all the way down here. So we end up with an oxonium. Now you've got a powerful electrophile, don't you? So now, in the next step, our methanol is going to come in and act as a nucleophile. So we have a methanol molecule, right? You've got an equilibrium between methanol and the protonated form. So you've got both species to work with. So now methanol is going to come as a nucleophile, do a nucleophilic attack, and there we go. So let's draw the intermediate that's formed. So we end up with, oops, mistake there. So we end up, come on, we end up with this intermediate here where we have two bonds like this. And now we have the protonated form of methanol kind of on the side here. So now we need to do two proton transfers to remove this proton and put another proton over here. So it's two successive proton transfers. So who's the base that's going to extract that proton? The base that's in solution is methanol, right? It's an equilibrium between methanol and its protonated form. So you're going to abstract this proton. So now you've taken care of the first part. So now we have hydroxyl here, OH here, and then we have OMe here. Okay, and now we're going to end up protonating one of those hydroxyls, doesn't matter which one, okay? So now you're going to take your protonated form of methanol, and you're going to, we'll pick this one, okay? So you're going to do a proton transfer onto here. Okay, so now you've created a good leaving group. So now we've got O2 positive here. And we've got OH here, and then we've got OCH3 like this. Now you want to restore the carbonyl. So to lose the leaving group, you're going to make a double bond here and lose water. So in this section, we're going to lose the water molecule, and we end up with this, where we have a new oxonium, and now we have OMe here. I should have written it as Me every time. I don't know why I replaced it with a CH3 here. Try to be consistent since we're learning the subject. And then in the last step is just going to be a proton transfer. So, oops. The last step, we have a proton transfer. And so methanol is going to behave as our base. It's going to pull off the proton like this. And we end up with the final product. And so we end up with is this guy here is our methyl ester. And that's the entire mechanism of Fischer esterification. All right. So there you go. There's the mechanism of Fischer esterification. So remember, the acid is going to be the protonated form of methanol in this case, and the base is going to be methanol in this specific case. All right. There we go. So give me a thumbs up if you're with me on Fischer. Isha. All right. Again, one of the most important mechanisms in all of organic chemistry. And it's going to take me a million years to find it in my slides again. I don't know where it was, somewhere. Hey, what do you know? It was pretty close. All right, so here's the mechanism written in the textbook, but I just went over the whole thing with you from A to Z. So let's move on from there. And there is actually proof of this mechanism by doing a radio-labeled experiment here, or maybe not radio-labeled, but isotopic labeling here, where they put in oxygen 18 in the methanol, and then it shows up incorporated into the ester. So it's a proof. And I've brought this up to you in class before. This is a Dean-Stark trap here. Gun. This is a, well, that's ugly. This is a Dean-Stark. It's a Dean-Stark apparatus is the proper term. But the bottom line is this is what you would use to run a Fischer esterification. I'm not going to go over it now on a summer afternoon because I think we're all kind of tired. But It's the way that you trap the water. The water goes into the Dean-Stark trap, and that's how you drive the reaction forward, is by removing the water from the reaction mixture. And it's a pretty clever way of doing that. So besides Fischer esterification, have we seen any other ways of making esters? Well, yes. One of them we covered in section 20.8. And you're like, hey, I already learned this today. There you go, repetition. Yeah, absolutely. Right? And again, the reason why we need pyridine, okay, is to neutralize what? To neutralize the HCl that's formed. HCl formed in the reaction mixture. Okay, so now we've learned 3 different ways to make an ester, okay? How many ways to make an ester? I wish there wasn't question marks on top of all these. It would make it a little bit easier. But let's kind of review all of them. If you wanted to take benzoic acid, so this is benzoic acid, and you want to convert that to ethyl, this is ethyl benzoate. Benzoate. Anybody have an idea how you would do this? You can even just name the reaction. I'd be okay with it. Anybody? How would you make ethyl benzoate? 3 possibilities. One would be Fischer. Yeah, you could do the Fischer reaction. So if we did Fischer esterification, we would need ethanol. We would need an acid catalyst, so a strong acid, and you would lose water, right? So that would be Fischer. All right. Anybody get another one? And it's kind of hard to scribble them in here, but we'll say the second one would be, first step would be sodium hydroxide to make the carboxylate, followed by ethyl iodide. So that would work. And the other one that we covered today is in step 1 to make the acid chloride using thionyl chloride, so SOCl2. And that means all you need is the alcohol, so ethanol and pyridine. So all 3 of these are a way of making this ester. And you've probably heard me say this already in class, but if you're sitting there wondering, why do I need to know multiple ways of doing the same reaction? Well, a good organic chemist should always have a couple of ways of doing something if it's possible, because many reactions are what we call substrate specific. It really depends on the substrate as to, how it's going to react. So a good organic chemist would try all of these and figure out which one is the highest yielding. All right, so that brings us to section 20.11, which is where we look at the reactions of esters. And I told you that there's 2 reactions of esters that are really, really important. I mean, all of them are important, but 2 that are mega important are acidic hydrolysis of an ester, which is not here, and then basic hydrolysis of an ester. And basic hydrolysis of an ester, okay, has its very own name. It's called saponification. So the saponification. And if you're thinking, well, that kind of looks like the word soap, this is how the pioneers made soap. So they saponified animal fat, so triglycerides, to make glycerol and carboxylates of fatty acids, and they would use that as soap. So this is essentially the principle of making soap. Okay, so they would take an ester, heat it up in sodium hydroxide. But the thing is, if you're doing step number 1, right, in a strong base, you're not going to end up with a carboxylic acid. That's impossible because you're in base. You're going to end up with a carboxylate, salt. And so in the second step, you have to acidify in order to produce the carboxylic acid, right? Acidic workup, the second step, is necessary to get the neutral carboxylic acid. Otherwise, you would have a carboxylate. Now, the mechanism of saponification, I'm going to put a big old star on this because this is such an important mechanism. And it's just a nucleophilic attack, loss of leaving group, and a proton transfer, right? This is the first part of the mechanism. Now, we get the nucleophilic attack, we lose the alkoxide as a leaving group, and then we do a proton transfer to make a carboxylate. So this is a carboxylate. So what's the second step? The second step is to treat it with H3O plus, aqueous acid, and what does that do? It does a proton transfer, and then we end up regenerating, forming our carboxylic acid like that. So you have to have the 2 steps, right? Step 1 is NaOH. Step 2 is H3O plus for a saponification reaction. You've got to have the 2 steps. So I said that an ester can be hydrolyzed under acidic conditions. Unfortunately, there's no SATSI name for this one. There's no like fancy cool name for this reaction at all. It's just acid hydrolysis of an ester. So now we take our ester, put it in aqueous acid, right? We're not driving water off. We're adding a lot of water because we're using aqueous acid, right? In one way, you're using the Dean Stark, and that's to make the ester, right? That was removing the water, but now we're adding a lot of water. And so if you understood the Fischer esterification mechanism, the mechanism of acid hydrolysis is just the opposite. That's based on what's called the principle of microscopic reversibility, is that if you have one reaction in one direction, the reaction in reverse is the exact same arrows, just in the reverse order. That's all it is. And again, that's based off of something called the principle of microscopic reversibility. So again, if you're looking at this mechanism and saying, hey, this is just the backwards Fischer esterification, it is. And so I'm not going to go over this in detail at the moment because I covered this in the Fischer, but you see that it's just a proton transfer, nucleophilic attack by water because water is in excess. Then we get 2 successive proton transfers to make the alcohol a good leaving group. We lose the alcohol, do a proton transfer, and we're all the way back at our carboxylic acid. And so this is definitely a mechanism that you need to know in this class. Now, another reaction of an ester is to do what's called an aminolysis. So to treat an ester with an amine, like ammonia, to make a primary amide, as you have shown here. It says the overall equilibrium favors the amide formation. Why? Because an amide is more stable than an ester. However, something of note about this particular reaction is the synthetic utility is limited. Okay, this isn't the greatest reaction in the world. It's actually very, very slow. So usually, if a person wants to make an amide, they would much rather make it from an acid chloride and then treat it with excess ammonia. That doesn't mean you don't have to know the reaction that's on here. It's just the one that I have written in red is preferable. It's just a preferred way of doing the reaction. Now, we've already seen the reduction of an ester using lithium aluminum hydride and then excess lithium aluminum hydride followed by water or aqueous acid, right? This was covered in chapter 12, the alcohol chapter, in detail. So there's nothing really new here at all. In fact, this mechanism was also shown to you in chapter 12. So there's nothing new under the sun on this one. This is all review. It's just in here repeated because it falls under the umbrella of carboxylic acid derivatives. So I'm not going to go over that in detail, but I will go over this reaction in detail with you. If you're wondering, well, can I reduce an ester down to an aldehyde the way I could an acid anhydride or an acid chloride? The answer is yes, but we don't use lithium. So remember lithium aluminum tri-T-butoxy hydride. I'm putting my hydride in the wrong spot. There we go. Son of a gun. There. We don't use this reagent. We use something called diisobutyl aluminum hydride. So let me write down that moniker for you since it's a pretty long name. So DIBAH, this stands for diisobutyl aluminum hydride. And this whole DIBAH, that's a new acronym for me. When I was a student, we always called it dibal, D-I-B-A-L, but anyhow, it doesn't matter. It's neither here nor there. If the book uses DIBAH, that's what we're going to use. So again, the second step, I'm going to erase the aqueous or water, and I'm going to put aqueous acid here. So diisobutyl aluminum hydride, you can imagine that it's just a less reactive form of some kind of aluminum hydride. And so it stops at the aldehyde and it reacts no further. And then we saw this reaction back in chapter 12, right? That you can react an ester with excess Grignard followed by treatment with aqueous acid. So I'll just scribble this out. aqueous acid in here. And again, there's nothing new here. You take the ester and you make a tertiary alcohol. And so I'm not even sure why he repeats this mechanism, because this mechanism was shown in chapter 12, and we actually went over it in that lecture. If you remember, you get a nucleophilic attack, loss of leaving group, you form a ketone, and does that react with a Grignard? Of course it does. So it reacts again, and you make a tertiary alcohol. And then again, in this section, you can just replace the water with aqueous acid like that, and that would fix the mechanism. All right, so now we have a question where we have a bunch of different esters or ester derivatives, and we're trying to do some reactions here. So what I'd like to do is take a short break and let everybody try these reactions. So I want everybody to give these a try, and I would also like you to try to draw this mechanism, because I am going to draw this mechanism from soup to nuts with you. Now this is a cyclic ester, okay, but it's still an ester. We call this a lactone. And so if we have an ester and we're an acid, acid is not a nucleophile. So what do you think the first step of this mechanism is going to be? To break that ring open, to hydrolyze this ester and acid. What do you think the first step would be here? Anyone? Exactly. Thanks, Audrey. It's going to be a proton transfer, isn't it? Right? So you're going to draw a hydronium ion like this, and you're going to get, oops, use my red pen. You're going to get a proton transfer, right? To render it susceptible to nucleophilic attack. Good. So what I'd like to do again is take a short break, and everybody, I would like you to try this question, and I would like you to try this mechanism. And then after that, we're going to get into the reaction of amides. And then after we cover amides, which is kind of not the most fascinating of the sections, but anyhow, we're going to cover that. And then we'll take a quick peek at nitriles. And then once we're done with nitriles, then we'll be able to say that we've covered all the chemistry in the chapter, okay? So we'll take a short break. We'll take a look at amides and nitriles, and that will at least have us finish the chemistry, so that on our next class on Wednesday, we can just practice some synthesis problems, and yeah, and that'll get us wrapped up with chapter 20.